Welcome back everyone to Linear Regression of PyTorch Part 2. We're going to continue right where we left off last time after we created our model class. Let's head back to that same Jupyter Notebook. Alright, here's the Jupyter Notebook where we created this model class. What we're going to do now is actually instantiate an instance of our model. So again, what we're going to do is in order for you to get the exact same random weight and random bias, at least the initial random weight and random bias, what we're going to do is again, set a manual seed here. Value doesn't really matter, so I'll just choose 59. Make sure you choose the same one. Then we'll say model is equal to model, and we have one incoming feature, that's the X, and one output feature, that's the Y. So this is just one simple pass, and what we're going to do is we'll go ahead and print out the weight. So off of this model, we're going to grab this linear layer. So recall that's the linear layer, and we saw a very simplified version of this up here. And recall that linear layer has its own weight and bias values. So we'll go ahead and grab that weight, and then we'll go ahead and off that linear layer, we'll also grab that initial bias value. So we go ahead and run this, and we get back this initial layer weight and bias. And note, since we chose the first manual seed of 59, if we come back here where we chose again 59, you notice that those first initial random weight and random bias from this linear layer, that fully connected layer, those happen to be the same value. So as models become more complex, it may be better to iterate over all the model parameters. So in order to figure out, well, what are all the parameters available off of this model, what we could do is the following. We could say for the name in param in, and what's nice about this is you can call named underscore parameters. And if you're wondering where this actual named parameters method comes from, it's because we inherited from the nn.module and we initialized it here. So we have model.nameParameters, and what we're going to do is we'll go ahead and print the name, and then we'll print out a tab space, and then call param.item. And if you run that, you get this nice little formatted weight, bias, and if you have a much more complex model, it'll print out the rest of the named parameters. But right now, these are all the parameters our model has because it's just a simple linear layer. Okay, what we're going to do now is let's go ahead and see the result when we pass a tensor into the model. So what I'm going to do is recall that our y value, if we come back up here, is defined as y is equal to 2x plus 1 plus those error terms. What I'll do is say, okay, if x is equal to 2, so I'll say a lowercase x here, torch tensor at 2, go ahead and print the model, and we'll say model.forward x. And so we get back this result where x is equal to 2. So you can confirm that, and if you want, you can also check out the corresponding notebook. We actually show the math for this. If you scroll down a bit, we show it right here, where if you plug in 2 to those values, 2 times 0.106 plus that bias term, that's equal to 1.175, which is what we get back out there. Okay, so that's the initial bias and initial weight value with a plugged in x value of 2. Let's go ahead and see how that performs for a variety of x values. And which x values should we choose? Well, if we look back to our plot, we should probably choose the x value range that we plotted against. So I'm going to go ahead and see for the values between 0 and 50 for x, what does our model actually predict that the y value should be? Keep in mind, we haven't actually set any loss function or anything, so this is off just an initial random weight and random bias. We should expect the model to perform very poorly because it hasn't learned anything. It just chose a random weight, it chose a random bias as its solution for fitting to this problem. So we'll go ahead and do the following. We'll say x1 is equal to, we'll say np linspace, and we're going to go from 0 to 50, and let's go ahead and grab 50 points. So those are my first initial x values. So I've chosen the first initial x values. What would our network here, which is essentially, it hasn't really been trained on anything, there's no loss function even yet, it's basically just a guess of this random weight and random bias. What would our model actually predict as y given this range of x values, which matches up with our data that we currently have. So given these x values from 0 to 50, what does the model think that the y should be? Recall, we haven't actually done anything yet. We haven't optimized, set a loss function. It's just based off that first random weight and bias, what does the model actually do? And again, it's going to perform quite poorly because it doesn't even know. So let's go ahead and define weight 1 as the very first weight value. So what was that first weight value? Well, it's right here. It's that 0.1059. I'll go ahead and just copy that as weight 1. What is our first bias value? We already have that here. Grab those digits. You don't have to grab the whole thing since we don't need to be that precise. And then we have our x1 value. So we're simply going to say our predicted y1 for those values of x is equal to our acquired on the first weight times x1 plus that first bias term. And if we take a look at y1, these are all the y predicted values for these x values given that first initial weight and bias term. How well did this actually perform? We shouldn't expect it to perform well at all since these are essentially just random guesses at first. What we're going to do is let's actually plot it out. We'll say plt.plot, and let's go ahead and plot out x1 versus y1. And so there's that plot. But notice the range here goes from 0 to 50, but 1 to 6. How does that actually compare to our real values? We'll go ahead and set our guesses to red, and let's plot those real values on that. So we'll say plt scatter, and we're going to copy and paste the scatter plot we did above here. So we'll say grab x numpy and y numpy. Remember, these are the true ones. So these are our real points. Let's go ahead and run it. And we can see here that the real blue scatter points, if you don't set any loss function or optimization at all, your model will essentially, just guessing off its first random weight and first random bias, perform really poorly. So how do we actually have the model learn, or at least try to optimize? What we need to do is we need to set the loss function. So we could write our own function to apply a mean squared error, but luckily the neural network function within PyTorch actually has this. So what we're going to do here is we'll say that our loss function is equal to nn.mse, mean squared error, loss. And by convention, when you're working with PyTorch and you take a look at the documentation, people label the loss function as criterion. And the reason it's called criterion is this is basically the criterion or criteria on which you're evaluating your function or your network's performance. So I'm evaluating my network's performance based off mean squared error loss. And later on we'll explore different loss functions that we can get off of this neural network library from PyTorch. But right now, our criterion for actually measuring how far off we are, that's going to be the mean squared error. So now we need to set an optimization. And this is where we're going to use stochastic gradient descent with an applied learning rate. And recall that the learning rate tells the optimizer how much to adjust each parameter on the next round of calculations. If you have too large of a step, then you run the risk of overshooting the minimum. If you choose too small, it's going to take a really long time to converge. So often with more complex networks, we have to play around with the learning rate a little bit. For this case, this is actually a really simple network. It's essentially just a linear regression. So we'll say that our optimizer is equal to, and off of this we'll say torch.optim, and here we'll say SGD for stochastic gradient descent. And the general method here is you just pass in off your model dot parameters, this method of parameters. And how do we actually have access to this parameters method? Well, again, like I mentioned previously, it's because we were able to inherit it from nn.module. Okay, so scrolling down, there's our optimizer, stochastic gradient descent. The last thing you have to do, if you do Shift Tab, you can take a look at the parameters. The required parameter is the learning rate, or LR. So here's where you have to actually kind of choose a learning rate. And for more complex networks, again, this is something you may have to play around with. A good starting point is 0.001. Again, if you see your model is taking forever to actually converge to something, maybe you choose a larger learning rate so it goes a little faster. Or if you're just really off, you may experiment with a smaller learning rate. Again, a lot of times this is due to experimentation. So we have our loss function and we have the optimization. Now we need to actually train the model. And with training the model, we have to choose a number of epochs. And an epoch is a single pass through the entire data set. So we want to pick a sufficiently large number of epochs to reach a plateau close to our known parameters where we actually set a known weight of 2 and a bias of 1. And if you scroll back to our original equation, when we were choosing the original x values and that original error, our true function is y is equal to 2x plus 1 plus this error term, which means that the network will hopefully try to get a weight as close to 2 as possible and a bias as close to 1 as possible. And the reason they're always going to be a little off from 2 and 1 is because there's error term exists there. So the network won't be able to perfectly do 2 and 1 because of this error term kind of fudging this data or adding noise to it. So we'll come back down here. So we have our optimizer, and what we're going to do is we're going to walk through the steps. So the first thing you have to do is choose a reasonable number of passes. And often this is something you have to experiment with, and the way you experiment is you actually kind of keep track of the loss. So I'm going to choose 50 epochs. This is actually probably too much for this simple problem, but the reason I want to choose a larger number is to actually show you how you yourself, for a more complex model, would kind of keep track of this. So we have epochs is 50, and then I'm going to create a placeholder list called losses, and that's where we're going to keep track of my mean squared error as I go along. And I'll say for I in range of epochs, so for 50 epochs, I'm going to say first I is equal to plus equal 1, and recall this is the exact same thing as saying I is equal to I plus 1. So for each loop, I'm adding 1 to I. And then I'm going to grab my predicted values. So I'll say y predicted values is equal to model running through the data in a forward step x one time. Then I'll say my loss is equal to criterion between my y predicted values and the true y values that I already know. So I'm calculating the loss, and then what I need to do is say my losses, and I'll append the loss at that particular epoch step. Okay, so right now all we're doing is we're predicting on the forward pass, calculate our loss, essentially our error. Then we're going to go ahead and record that error so we can see our improvement over time. And let's go ahead and then print out where we're currently at. So we'll say here, epoch, we're going to print out I. And then what we'll also do is we'll print out the loss. So here I'm just using some print formatting. The loss we'll say is equal to loss.item. And then we'll say the weight. And here I'll insert model.linear weight item. So we'll see how the weights and biases also adjust over time. And then we'll actually also print out the bias. So we'll say model linear, and then we'll say bias, and then item. Okay, so I'm going to zoom out just a little bit so you can see what we're doing here. Essentially, after each forward pass, after we get our prediction, calculate the loss, record that error, I'm going to print out what epoch are we on, what is the loss, what is the weight, and what is the bias. Now, how do we actually adjust the values? So how do we actually adjust weight and adjust bias? So what we're going to do is after we calculate the loss and then print out this current line of results, the gradients accumulate with every back propagation. So to prevent compounding, we need to reset the stored gradient for each new epoch. So what we're going to do is we're going to grab our optimizer and call 0_grad for the gradient. So again, that's because the gradients are accumulating with each back propagation step, and to prevent the compounding here, we need to reset that stored gradient for each new epoch. So that resets it. And then what we're going to do is actually perform the back propagation, which we do this off the criterion object, or the result of it, which is the loss, and then we call backward. And then what we're going to do is call the optimizer and call step, which then updates the hyperparameters of our model. So you're going to see loss.backward and optimizer.step being performed throughout this course because that's how we actually perform the backpropagation steps and the updating of our hyperparameters, which in this case is just that single weight and single bias. Let's go ahead and print this out, or actually run this. Okay, so here we see for each epoch, the current loss, the weight calculated, and the bias calculated. So what's actually happening here is you'll notice that when we first start off, we have a really large mean squared error. That makes sense because our initial weight, recall it was 0.1, and the initial bias 0.9, were just random guesses. But after we perform backpropagation and updated our hyperparameters, we reduce our mean squared error because we've updated our weight to something more reasonable, as well as our bias terms. And note just how now close, after just one step, the true weight should be equal to something close to 2. So we can see here it jumps from 0.1 to 3.3, and the true bias should be close to 1. And note that since it was already kind of close to 1 at 0.96 for that first random guess, it updates it just a little bit to 1.0. And then it goes through another epoch with those weights and biases. You calculate your mean squared error, and now you're performing a little better since your weights and biases were updates. Perform backpropagation, update the weight and bias again, and you're performing this over and over and over again. And then eventually, after a certain number of epochs, you should see your error begin to converge as your weights and biases stick to really similar values. So now, after about 15 epochs, your loss really isn't changing. It stays to 21 point something. You're getting slight improvements, so you're getting a mean squared error improvement of maybe like 0.01 or 0.001 after a while, but really, after about somewhere around the 15 epoch range, you're not really improving much. And that's because your weight and your bias term aren't really being updated that significantly. They're hovering around 2 and 1 respectively, which recall were the true terms. So if you're running a really complex model, it's a good idea to every once in a while print out your loss for a particular epoch. And it's not super important to keep track of your weight and biases for more complex networks because you'll have lots of neurons, which means you have lots of weights and biases to keep track of. So it's more important to just kind of be printing out your loss and seeing if you're hitting a convergence, then that's probably all the epochs you need to train for. Now recall that we were actually keeping track of these various loss values over here when we were appending that particular error or that loss. Let's go ahead and plot it out, and we'll actually be able to visually see this convergence to 21. So I'm going to come back down here, go ahead and zoom in just a little bit, and your formatting may get messed up if you start zooming in too much, so just keep that in mind. We'll say PLT plot, and for a range of epochs, remember we ran for 50 epochs, go ahead and plot out the losses, and then I'll give this a little Y label. So the Y label will be the actual mean squared error loss, and the PLT X label will be the epoch. Recall that the epoch is one complete pass on the training data. So we run this, and we can see we start off with a really high error, and then as we go down, we eventually, after a certain number of epochs, begin to converge to some sort of minimum loss. And now finally, let's go ahead and use the model because we have our finalized weight and our finalized bias values. So what we're going to do is set up our prediction equation first, and then we'll fill it in. So we can say that our predicted y values for any series of x points is going to be equal to our current weight times that particular x value, or the array of x values, plus the current bias term. And how do we actually get those x values? So we need to set x equal to something, we need to set our current weight equal to something, and we need to set our current bias equal to something. So for the x values, this can be 1x if you only want to predict one point, or if you want to predict a range of points, this can just be np length space, and then whatever values of x you want to predict for. Let's just go ahead and predict, just as we did before, for 50 values of x between 0 and 50. Then what we're going to do is grab our current weight. What is the current weight? It's simply saying model.linear.weight and grab that item. Similarly for the bias, it's again just call model.linear.bias.item. And so when we run this, for these x values that we made, just as we did last time, we now have our corresponding predicted y values. How well did we actually perform? Let's go ahead and plot them out. We'll simply say PLT scatter, do the original values so we can compare them directly. So there are original tensor values being transformed to NumPy arrays, just as we did before. and then we can plot out our prediction values where we have x against that predicted y. And if you want, you can scatter plot those too, but for this, I'll just go ahead and make it a line plot. We'll make it red, and then let's go ahead and run that. And you can see that our predicted values pretty much perfectly predict that underlying model of y is equal to 2x plus b. And then that error term we can't really account for because it's random noise, but this is a pretty accurate model or an accurate guess because the true values it should have predicted were 2 and 1. And if you see, the actual values at the end are 1.98 and 1.05, which is not bad, especially considering that you had that noise. All right, thanks, and we'll see you at the next lecture.